Okay, hello everyone. So we will continue the discussions from where we had left in the last class. Today we'll be discussing the statically indeterminate situations, and you are already aware what a statically indeterminate situation is. Okay, so let's see example 2.9. In this example, you have this figure shown in front of you. There's a pendulum of a clock. Okay, so this is the clock. Then there is this pendulum which you see, and they have that weight is 12 Newton. It's given in the question, and it is suspended by three rods, 760 millimeters in length. So as you can see, there are two rods which are made of brass. Okay, the first and the last one, and the middle rod is made up of steel. So clearly you have a case in which there are two different materials involved, and they would, I mean, just the sight of it you can figure out that they will have different elasticity modulus for you. Now you have to know how much the 12 Newton suspended weight is carried by each rod. Okay, so 12 Newton is carried and shared between these three rods, and how much is carried by each. Okay, so let's look at the model of this. Okay, this is the actual situation. This is the model of it. There are some assumptions which you make. So you assume that the support at the top and the weight at the bottom are stiff and act as rigid members. So this is rigid, and the weight which was here is rigid. Okay, meaning there is no deformation in the this support and the weight. The only deformation which happens in this system, in this pendulum, is in these three rods. Okay, now you can also see there is a symmetry of the rod arrangements and the loading, and each brass rod will carry the same load because the brass rods are at this end and this end, and there is symmetry in this one of the geometry and the loading. So this is something which you had perhaps again seen in your mechanics lectures last year. Symmetry in geometry and loading. So the brass ones will carry the same weight, and obviously all three of them will have to elongate by the same amount, right? So these three rods have to elongate by the same amount, otherwise the clock will get tilted. Okay, so that's what we do now. So we'll start with the three steps of 2.1, the equation 2.1, which was the force equilibrium, and you will balance the forces in the y direction. That would be equal to 12, will be equal to Fs plus Fb plus Fb. Okay, there are two brass rods. Then you go for the geometric compatibility. That is delta S is equal to delta B. The extension in the steel rod will be the same as that in the brass rod. And the last is obviously the force deformation relation. So this is where you employ the Young's modulus. So you will say for the steel rod, delta S, this is the Hooke's law, okay? Fs, Ls, As and Es. Similarly for the brass one, you would write Fb, Lb, Ab and Eb. So you will find the the elasticity modulus from the table. Area is already given to you, which is So the diameter is given, you can convert it into with the pi r square into the area. Okay, and then you will have the length, which is also given in the diagram. I think there is slight error in the book. You can check the actual calculations about how the areas are calculated, but you always know, I mean, you know the diameter and radius, you can find the area. You have to assume a circular cross section. Okay, so that's what how you would solve a statically indeterminate situation. It's called statically indeterminate because you couldn't have solved it just by knowing the forces. Okay, and that's where this idea of statically indeterminate is coming. Okay, now let's move to the next sort of example. In this one, which is example 2.10a, there is a figure over here. This shows an instrument suspension consisting of two aluminum bars and one steel rod. So these are the two aluminum bars, this one and this one. Okay, it's already shown by a diagram also. So the dimensions are given. I think in the imperial units you will have to convert it to the SI system, and then you have one steel rod mounted in a stiff frame. So this is the steel rod and it is mounted on the stiff frame. So this is the stiff frame. When you say stiff frame, please don't confuse in a way that everything has a stiffness and everything has a Young's modulus. Even in this example, the weight was assumed to be stiff. The idea is it is much stiffer compared to the other things. Hence, the Young's modulus of this would be much higher compared to, say, the aluminum and steel, and in the previous question, steel and brass. So this has to be assumed as rigid, meaning no deformation happens in the stiff frame, sorry. Okay, and there is also a spring EA which is inclined at 45 degrees to BA. So this is the spring EA which is inclined at 45 degrees to BA. So an assembly, in this assembly you are already aware that there are parts of a machine, they are put together and then that is called a assembly. Okay, so all the parts when you put together it becomes an assembly. So perhaps in some modeling tool you will learn these terminologies in a much greater detail. Okay, so in assembly the nut on the EA is installed with sufficient extension to produce a force of 50 newtons. Okay, so there is a nut on EA and it is installed with sufficient extension to produce a force of 50 newtons. So you already know how much force the spring will be having. Now you want to find the deflection of the joint A, this joint A, relative to the frame. So the frame is clearly rigid, so it doesn't move. So that's why you have taken a system, the frame which does not move, and hence you must find the deflection with respect to this frame caused by the spring loading. Okay, so you have to see a model of this problem. Okay, that is shown in this figure 2.15b. You assume that the frame is rigid compared to the aluminum and the bars and the steel rod. Okay, this is something which you are already been told. By the way, there is a in the previous question I knew it was a circular cross section because in the question it is given as a rod. Okay, so that's one way you can sort of get a hint that the cross sectional area was circular. Anyways, so in this problem it's already, I mean, as we have discussed, the frame is essentially rigid with compared to the aluminum and the steel, and thus the points B, C, D can be considered as fixed. So B, C, D are considered as fixed. Okay, and you have shown this by this symbol. It means a wall, fixed wall. Okay, and the deflection may be measured relative to these fixed points. Okay, so now the frame is out, and that you have just modeled by these three fixed points. Now you must consider the steel rod to be pinned at D. Okay, this is a good approximation since AD is such a slender member. Its length is 53 times its diameter. So if you look at the question, you can find that AD is a slender member, meaning the length of this is very large compared to the thickness. Length is much larger compared to other dimensions. Let's put it this way. So this is called a slender member. Okay, so it is said that you can assume D to be a pinned. So this is a approximation because it's not actually told in the question which kind of a thing is there on D, which kind of a joint is there on D. Okay, so it's an approximation to take this as a pin because it's a slender member, and any rotational restraint offered by the nut and the washer will be negligible. So you have a nut and a washer over here. First of all, if you do not know what a nut or a washer looks like, please go to the internet, search this in any search engine and click on images. You should know what a nut and a washer and a bolt looks like. Okay, these are the three things which you should all be aware of how they look like. Okay, what is a washer, why is it used, and so on. By this stage of any engineering course, I think you should be knowing all this. So I think if you don't know, perhaps it's now is a good time to learn about it. Okay, so the idea is because of the nut and washer on this D and it being a slender member, you are assuming it to be a pin joint. And you have, why are we trying to get a pin joint over here? Because it is easy, we are comfortable. We have already seen that despite having friction in a pin joint, you can exclude the contribution due to the moments due to that friction, since the dimensions of the pin are quite small. So that's why we are trying to approximate as a pen, and we are able to do it given its geometry in this case. Now you assume that the action of the 50 Newton spring force will be to move the point A to a new position A dash. So this is the 50 Newton and it moves to a new position which is A dash over here. Okay. So, and this coming from A to A dash, you have to move vertically downwards by delta Y and then horizontally leftward to delta X. That is what we are assuming. And this is what we have to eventually find, the value of delta Y and delta X in this question. Okay, so since we have now drawn a nice model like the previous case, all we now do is write the geometric, the first is the force equilibrium, which is coming from the equation 2.1, force equilibrium. So you assume that the forces in the members AC and AD are tensile. This assumption to start off with, which comes from only intuition, and this you will develop as you progress in this course. Even if you are wrong, there is no problem. All you do is as long as the tensions and compressions are consistent, the forces are consistent, you will at worst get a negative answer, which means your initial assumption was wrong. Okay, it was just the opposite of it. So you don't have to worry too much about it. So AC and AD are tensile and they are assumed to be, in this case AB is assumed to be compressive. Okay, so this intuition should come from the fact that the spring is trying to pull the point A in this direction, and hence AC and AD should be in tensile. That's where we are getting it from. Okay, so for the free body diagram, so this is the free body diagram which you have of the joint A over here. This is the FBD of the A. You have the force AC, you have the force AB, you have the force AD. So the directions are coming because this is tension, and this is compression. Okay, and this is FBD of the joint A, and 50 newtons is again from the spring, and the deformations are already shown. So all you have to do is balance the forces in the x direction and then balance the forces in the y direction. Similarly, for the second step of a geometric compatibility, okay, so you have to read it in this way as is given in your book, that the deflections will be very small, and this is what we start off as we said earlier in this course. The deflections in the linear elasticity can be assumed to be very small. Large deflections we don't deal with this in this course. Okay, so linear elasticity and linear behavior of stress versus strain, you always assume that the final deflections are very small, the actual final deflections. So the deflections will be very small compared with the lengths of the bar, okay, and thus the using the approximation which was developed in example 2.4. So if you go to example 2.4, okay, I'll just go over here. This was example 2.4. And what was the approximation method which we developed? That rather than taking an arc, we will actually take a tangent. Okay. So rather than taking an arc at this D1, we took a tangent. Rather than taking an arc at this D2, we took a tangent. Okay. So the same approximation we'll apply over here. And the language of all this is very important. I mean, because the deflections will be small compared to other dimensions of the stressed and the deformed members, that is why you are approximating these arcs by the tangents. Okay, so you can approximate this, and hence you can just move the bar in the tangential direction, and that you get a delta y and delta x. So in this case you will have a delta AC will be equal to delta y, and delta AD will be equal to delta x, and obviously delta AB will be equal to delta x. Okay, so this is the geometric compatibility which you have in your question. The delta AC, the change in this length, okay, will be delta y. The change in AD will be equal to delta x, and also the change AB will be the same as delta x. The only difference is AD will extend, hence delta x can be calculated. In this amount, the same amount will get compressed. So the delta x is the compression in this case. So this is extension, extension, compression. Okay, now the last part is obviously the relation between force and deformation. So you can find delta AC is equal to FLAE by AC, and delta AD similarly you can find using the Hooke's law, and you can find delta AB in a similar fashion. Young's modulus you will find from the table, and don't worry too much about getting the exact value of Young's modulus. I mean, there would be no doubt when and if you are asked about this. So normally it's a range. I mean, for example, steel, as you know, is a mixture of iron and carbon. Depending on what other elements are present or what is the percentage of carbon, this Young's modulus may vary slightly here and there. Okay, so you don't have to worry too much about these things at this time. Only thing is, what you must focus is trying to get these values from a table if it's given. Okay, and whatever value you choose from that range, it's all acceptable. The method here is more important, and take the units very carefully. Please never report anything without a unit. Don't report any vector without a vector sign. Okay, so after this there is some discussion about the computer analysis of a truss structure, which is section 2.6. Since all of you have done a basic course in computer programming by this stage, I will leave it to you to study this computer structure, computer analysis. You can do it in MATLAB or any other programming language which you like. So the book has an example from MATLAB, but you are free to use any other software like Python or whatever else you are comfortable using. And you should try to definitely code this yourself so that you are comfortable with the idea of using a computer for solid mechanics problems. Okay, and they do come in handy at later stages of your course because it only improves your understanding about mechanics. Use of a computer programming will only improve your understanding about mechanics. Okay, so let's move to something which requires us a slightly more involved discussion of energy. Okay, so the topic is the section 2.7, elastic energy and the Castigliano's theorem. And this is a very powerful tool in trying to solve problems in mechanics. And we'll go through the fundamentals over here, derive and actually use the Castigliano's theorem, and check how this works. One of the other important things is later on many of you will take up a course called finite element analysis. I mean, you can either take it, I think, for in mechanical engineering department or applied mechanics department or wherever, maths department. I don't know which department you would want to take that course, but many students take that course. And it's a computational course in mechanics, and the foundations lie in this section which we are about to discuss over here. So we won't actually use that, but the foundations definitely are shown over here. Okay, so let's see this. Okay, so you give a brief introduction, we give a brief introduction to the concept of energy and develop a powerful tool for calculating deflections of elastic systems. Now, the work done by a force vector F when its point of application moves through a displacement vector ds is the scalar or dot product. So you are already aware that the work done by a force vector F when its point of application moves through a displacement vector ds. So this is a dot product. Okay, and you are aware that this can be written as F cos theta, F cos theta ds, and where theta is the angle between F and ds. Okay, now in general F will vary as the point of application follows a certain path. Okay, so the total work done by F is given by this integral. Okay, so let's call this as a small work, and the total work done is integral of F dot ds. Because F is a variable force. Okay, so and by saying that F will vary, it does not necessarily mean that the F will vary in magnitude. Since it's a vector, a variation in the direction as well counts as a variation in the force. So even when the magnitude remains the same, the direction is changing, it is still said that the force is varying. Okay, so now when this work is done by an external force on certain systems, their internal geometric states are altered in such a way that they have the potential to give back equal amounts of work whenever they are returned to their original configurations. You are already aware of this. So you are already, for example, aware of what a conservative what a conservative systems are, and the work done in this case is stored as the potential energy. Okay, you already aware, for example, the force of gravity is you raise a block of wood or a pen or whatever you would want by a certain height, and that is stored as a potential energy, and you can have it back, right? In a conservative system you can have it back whenever you want. I mean, if you let it fall, it will convert itself into the kinetic energy and so on. Similarly, that also applies to electrical systems. When you have a charge and then you do the work by taking unit charge away or towards a given other charge, and then there is energy which is stored over there, that's another form, and so on. So these are all conservative forces. And compare that to the force of friction. Friction, as you are aware, is a non-conservative force because there is no way to get back what you are doing work as an external agent. Okay, so this is all applied and applicable about with respect to an external force. The lifting of the block was through an external force. The moving of a block on a rough surface is also through an external force. This is called a non-conservative. You are already aware of this idea. Now let's move ahead and consider elastic but not necessarily linear spring. Look at this case. It's a non-linear spring. That's the first thing which we are doing. Meaning the relationship between F and the displacement of the spring is not linear. So it is not, it is not like this where the slope of this is k. Okay, it is not like this. It's a non-linear spring. That is what you have taken over here. And so now let the springs undergo a gradual elongation process. Okay, so this is an important part, a gradual elongation. Why gradual? Again, we have already discussed, to ensure quasi-static situation, meaning every point of this elongation, every stage of this elongation is in equilibrium. So there is no acceleration at any stage. That's the meaning of this gradual elongation. And we did the same when we were trying to pull a material of length A and area A, and we drew a graph of force versus deflection there, force versus displacement over there. Okay, so the external force over here is clearly F, and the elongation is denoted by the sign delta. The potential energy U associated with an elongation delta is defined to be the work done by F in this process. Okay, so the potential energy in this case is equal to F dot ds is equal to 0 to delta, which is the final elongation or the elongation at that stage, and it is written by this. So potential energy will show by the symbol U, and it's a scalar quantity clearly because this is a dot product. So the dot product of two vectors is a scalar. Okay, so this is something perhaps which you already knew. Now there are a few things over here. This fact that the work done by this external force is stored in the potential energy actually comes from the first law of thermodynamics. I hope you have a course in thermodynamics at some point where you learn about the first and the second laws, and you will also learn that for any process to happen, look at the textbook. It mentions that elongation delta is defined by the work done F in this process. Okay, just before this equation 2.4, 2.3. So according to the laws of thermodynamics, first law alone is not enough to ensure that a process happens. So that process must satisfy the first and the second law itself. This is just to sort of initiate to you why all these courses are linked to each other. So this comes out from the first law of thermodynamics, and perhaps whenever you learn that course, you will learn about it in a much greater detail. There you'll also have a component of heat coming in or out of your system at that place. Anyways, for now you can take it in this form, and then you go to figure 2.19b, this one. The energy appears as the shaded region shaded area under the force deflection curve. So you already knew this. I mean, the integration of these quantities would mean that you are finding the total area under the curve. And if this spring should happen to be part of a larger elastic system, it will always contribute the energy 2.3 to the total stored energy of the system whenever its individual elongation is delta. Okay, so if the spring is a part of a larger system, and how can you see that? The most easiest example is to consider these pens which you have with a spring, right? I mean, you press the tip from the top and then the nib comes out, and then you can write, and when you don't want to write, you press it again from the top. The spring will come into action and the nib will go back into the pen. So that is an example where you can see that the spring is part of a larger system over there. Okay, and the concept says that it will always contribute the energy, this energy 2.3, to the total stored energy of the system whenever its individual elongation is delta. So whenever you press that spring into compression, you have this energy which is available and which is stored, and it is available for the larger system. Now the magnitude of this energy is sometimes an important consideration for in mechanical designs. Consider that you were trying to design the same pen which we are talking about. You really want the energy which is stored during compression to a certain in a certain range. I mean, it should not store a very large amount of energy. It should not store a very small amount of energy for any design to work. So that is something which you take care of as a designer. Okay, so because it is something which is absorbing energy, so it has a capacity to absorb energy, just like every battery has a capacity to store how much energy it can store. Okay, similarly a spring also has its capacity, so you must as a designer take care of those things, that which spring to put, and that is determined by the material which you put in the spring and the number of wounds it has and so on. Okay, now let's come back to the newer part of it and look at this 2.20a. Okay, this is a general elastic structure. It can be loaded by an arbitrary number of loads. Okay, so you have these pi, and all these arrows are arbitrary number of loads, and at a typical loading point ai, so this is a loading point ai, so a1, a2, a3 and so on, meaning at a1 p1 will act, at a2 p2 will act, and so on. Okay, many of them can be zero, in the sense if you call this as a2, here P2 is there, but its value is equal to 0. So there is no force acting at this particular loading point. Okay. So which can be, and the displacement and the equilibrium displacement due to all the loads is SI. Okay. So the displacement is SI over here. So vector, that's why it's showed in a bold sign in your textbook and the diagram in front of you. Okay. So if during the loading process the displacements SI are permitted to grow slowly, again for the same reasons, through a sequence of equilibrium configurations, the total work done by all the external loads for this elastic structure would be, so total work done would be equal to, and these are all external forces, so they go from 0 to SI, which is a vector pi vector dot dsi vector. Okay, and this total work done will be stored in the form of potential energy in this system. Okay, so that's why I'm writing it equal to u. All this is stored, all these work done by the external forces at various points, loading points, is stored as a potential energy. Now you introduce the concept of a complementary work. And complementary energy, and so that you are able to obtain a result which is parallel to this 2.4. Okay, so you want to get a result which is parallel to this result 2.4 for this elastic structure which you have over here. Okay, now let's see what a complementary work is. You already know what work is. I mean, you have already seen this over here. Okay, this thing. You want to write a complementary work. So when the point of application of a variable force F undergoes a displacement S, the complementary work is, so the complementary, let's see, dWc is equal to integral of S dot dF. Okay, you can see the difference between this work and the complementary work. It's in the definition, it's how it is defined. Okay, and so the when complementary work, and by the same arguments, when you do a complementary work on certain systems, their internal force states are altered in such a way uh, that they are capable of giving up equal amounts of complementary work when they are returned to their original force states. Compare this to the previous definition. In that we said that when work is done on certain systems, their internal geometric states are altered. Okay, in such a way that they are capable of giving equal amounts of work when they are returned to their original geometric state. So that is the definition over here. So here you are coming back to the, in the complementary work, you are coming back to the original force state. There you are coming back to the original geometric state. Under these circumstances, the complementary work done on such a system is said to be a complementary energy, and then it's a very similar argument after this, that you consider the gradual loading of a non-linear spring. This non-linear spring, figure 2.19a, the complementary energy associated with force F is defined to be the work S dot dF equal to 0 to F delta dF with a star. Okay, so the star symbol shows a complementary work, and you can also, there is some level of abstraction in trying to define this complementary work, but you will have to be very clear of the definitions. If you try to remember it as a formula, you will always go wrong. Please read the definition, the textbook which you should be reading, and it will be very clear how these are different, and there is a need for them to be different, which will become very clear in the minutes to come. Okay, so you have already defined now the complementary work done by F, and this, if you look over here, is actually the area above the curve. Okay, so you have this dF over here, there's a dF over here. Earlier you had a d delta, and this was d delta. So this is this area under the curve, or for a small strip you would have this value. Okay, and again, I mean, if this spring should be happen to be a part of a larger elastic system, it will always contribute to the complementary energy. In the earlier case it was called the potential energy, here you call it the complementary energy. And it's anyways a definition. I mean, potential energy perhaps something you are more comfortable with, but you didn't actually question it so much. So it was just how you were defining, because this part was comfortable to all of us because you had seen this before. Complementary energy may be slightly abstract or new because you have not perhaps seen these language and seen these definitions before, but it is the same way you are defining it. It's just that in one case you have the geometry which is changing of the system and coming back to normal. In this case there is a force system. So if force is starting from 0 going to F and coming back to 0, then that complementary work is given out. Okay. Okay, now you please come back again to this general elastic system. Okay, and to facilitate the calculation of complementary work, we show in figure 2.20b over here. Okay, so 2.20b, the displacements SI decomposed into components parallel and perpendicular to PI. So this SI as a vector has a component parallel to the applied force and perpendicular to the applied force. Okay, so you have broken this down into two components and now you can treat them separately. So delta I is the component of this displacement which is in line. So delta I is the inline component, meaning it is in line with the force which you are applying, external force which you are applying. Now if the loads in this figure are gradually increased, the total complementary work done by all the external loads will be equal to the total complementary energy. Just like the previous case, you take all the i's, go from 0 to pi, si dot dpi, this is equal to summation 0 to pi delta I dpi equal to u star. Okay, so this is stored by all the internal elastic members of this, and it's the complementary energy shown by this u star symbol. Now the energy functions u and u star have many uses in mechanics, and they are this extensively used in something called the variational principles, which is the starting block of FEM. Okay, we won't discuss neither this principle or FEM for that matter, but just to give you a hint what a variational principle is from something which you already know, and this complementary energy are used over there is like these two situations. You have a ball over here, and if you slightly vary it, it will be unstable, it will fall off. Okay, and similarly if you have a ball over here, if you slightly vary it, the displacement over here, the position over here, it will come back. In the sense, this is stable, this is unstable. You knew this. Okay, one other example is that if there are 2 points, okay, and then you connect them by many curves, say this curve and then a straight line, you know that this straight line is the shortest distance between these 2 points. Okay, now the variational principle applies to over here, saying that if you slightly vary this curve away from this point, away from this straight line, no matter by how small degree, you will always get a length which is greater than that which you had got by the straight line. So these concepts are, these ideas are used in variational principles and in a much grander scheme, and perhaps this course is not there for this, but just to give you an idea about what variational principles used in FEM are. So perhaps you will take a very nice course sometime in your 4th year. Applied mechanics does it. I'm sure mechanical engineering would also do that, and perhaps civil engineering, every department does that. Okay, now we want to actually not do this, we want to show the something else which is called the Castigliano's theorem. So to do that, let's look at 2.6. So 2.6 was actually this was 2.5. Okay, so you have a system like this which is 220A, in its equilibrium position with the complementary energy 2.6. So this is the complementary energy 2.6 for this system, and you consider a small increment delta pi to the load pi. So to this load pi, you consider a small low increment, an increase in this load, while all other loads remain fixed. Meaning, if you have chosen that P1 with the appropriate direction, should actually become P1. Sorry, so the direction is fixed. Okay, we are not changing the direction, so I'm only writing it as a vector scalar over here. So Pi has an increment delta Pi, and all others are fixed. Meaning, if you have say 4 loads P1, P2, P3, P4, so P2 becomes P2 plus delta P2, but everything else remains the same. And clearly, at which point does this act? It acts at the point A2, A1, A3, A4, and so on. So this is what we mean by an increment delta Pi, while all other loads remain the same. Okay. So this will cause this delta Pi increment in this force will change slightly. The internal forces will change slightly to maintain the force equilibrium, and increase in complementary work will require an increment in the complementary energy. So for a small delta Pi, you have this delta Pi, this is the work done. Okay, and you see that you are taking Pi and delta I because only the inline component will act as a work, the perpendicular one will not. So that will be equal to U star, and this implies that delta of U star by delta of Pi is equal to delta I. Okay, so an increment in this work, external work, will be shown as a increment in the the complementary energy of the system. So the energy of the system was U star, and now it has become U star plus delta U star. Okay. Okay. So if the limit, I mean, if this increment is actually tending to 0, you can write that delta I is equal to dou U star by dou Pi. Okay, from here you can do that. If delta, so this is just a definition of what a derivative is, and we are using the symbol dou over here just to indicate that this is a partial differentiation. So u can be a function of many things, and here u can be written in form of p, the loads, and other things as well, but you derive it with respect to the loads. So this is called Castigliano's theorem. Okay, and this clearly, as you have seen, does not assume linear systems anywhere. I mean, we started off with a non-linear system. Okay, so what this tells you is that you can find the displacement, inline displacement delta I, if you have the complementary energy written in terms of the loads. Okay, so in a very similar manner, if you have the not the forces but actually the moments, then you can write the Castigliano's theorem as this. Where the mi is the moment vector, phi is the angle of rotation. So it's like an angular displacement component. Okay, so this is where we sort of leave this with. Now it so happens that if you have a linear system, okay, just come back to here. If you have a linear system for say the spring, and that would look like this. So the area U will be the same as U star. Okay, so for a linear system, U will be equal to U star. So the Castigliano's theorem can be written as delta U by dou u by dou pi, because u star is equal to u for linear system. So this course, as I have said, will be only about linear systems, hence our Castigliano's theorem is this. So we will use this in the problems for the next class to find the inline displacements using this Castigliano's theorem. And I leave you with this note which I had learned from somewhere. I mean, you should definitely check it, that Castigliano invented this theorem or came up with this theorem in his undergraduate studies, which is where you are right now. Okay, so I think you should definitely fact check it from somewhere and let me know whether it's true. Okay, I haven't done that, so you should fact check it whether he did actually come up with this in his undergraduate studies. That should be a great motivation for you to study mechanics. Okay, and you will see the use of this in the next class. So thank you.